This video is presented to you by the students Jimena, Silvia, Daniel, and Jorge about the identification of saponins in horizontal using supercritical fluid chromatography with an MS detector.
As in all chromatography, individual components of complex mixtures are separated from each other by differential interaction between a stationary phase and a mobile phase. Supercritical fluid chromatography is a variant of high-performance liquid chromatography, in which a supercritical fluid is used to replace the liquid mobile phase. The fluid must act as a solvent for the solutes of interest. A supercritical fluid has properties intermediate between those of a liquid and a gas. The temperature and pressure of a component in its supercritical state should be higher than the critical values. The critical temperature of a substance is the temperature at and above which vapor of the substance cannot be liquefied, no matter how much pressure is applied. The critical pressure of a substance is the pressure required to liquefy a gas at its critical temperature. When a component is in its supercritical state, it cannot be liquefied by increasing the pressure. SFC is often employed for separations involving non-volatile or thermally labeled species that cannot be separated by gas chromatography or liquid chromatography. It is also a powerful technique in the separation and analysis of chiral substances.
SFC combines liquid and gas chromatography technology. The sample is carried through a separating column by a supercritical fluid that works as a mobile phase, where the sample is separated. A supercritical fluid is any substance at a pressure and a temperature above the critical point. This has the best characteristics, spreads like a gas and dissolves as a liquid. Carbon dioxide is a perfect example of the supercritical fluid because it's non-flammable, non-corrosive, and has a limited toxicity. It is also cheap and it is miscible with most organic solvents.
The main components of the supercritical fluid chromatography system are as follows. The mobile phase is comprised of CO2 and, if required, a solvent or modifier to increase the solvation power. The stationary phase, depending on the compound of interest, the desired column is selected. For SFC, there are packed, capillary, or even chiral columns for the detection of enantiomers. The pumps are necessary to get to the supercritical point. The type of pump depends on the selected column. For packed columns, reciprocating pumps are the most widely used. For capillaries, syringe pumps. They help for easier mixing of the mobile phases in addition to providing the constant necessary pressure. The injector is necessary to integrate the sample into the system. There are loop or inline injectors. Depending on the pressure of the pump, you can select one or the another. The oven is required to maintain an accurate temperature of the mobile phase when in the column. The detectors, HPLC and GC detectors like optical, flame, and spectroscopic detectors can be used. Restrictors or back pressure regulators are used to maintain the desired pressure in the column and to convert the mobile phase in the supercritical stage to gas for the detection.
Now we know the main components and equipment, but you ask, how does the technique work? Step 1. In a solution that sweeps the mobile phase into a tube or column, the sample is injected into a high-pressure flow stream filled with fine particles. Step 2. The individual components in the sample interact differently with the surface of the particles. Step 3. The sample is separated in time and space as they pass through the column. Step 4. The components emerge from the column at different times as Gaussian or pseudo-Gaussian peaks. Step 5. The detector can identify the components in the sample for its further analysis. The examples of main applications with this technology has been studied in many countries around the world. As we can see in this heat map, United States and China are constantly investigating about the supercritical fluid technology, as well as Mexico, Brazil, and most of Europe. The trends are leaning towards the analysis and purification of fragile molecules, for the synthesis of synthetic drugs due to its capacity for complying the requirements of good manufacturing practices. Bioanalysis applications focus on pharmacokinetic studies, while forensic applications can identify drug abuse. Also, the identification of pesticides, emerging contaminants, and halogenated pollutants in wastewater are some examples of applications for the environmental sector. The food science and natural products sector relate to each other since most researches are focused on the extraction and purification of bioactive components from plants and then implemented in food to enhance them. Some examples of compounds that can be extracted or analyzed are polyphenols, triterpenoids, carotenoids, and lipophilic vitamins. A novel application of supercritical fluids in the food industry involves the extraction of saponins in horizontally. Saponins have health-promoting benefits and they are currently used in foods as natural surfactants and preservatives. With supercritical fluids, they can be easily separated from the sample with high flow rates and high efficiency. However, due to the weak or no UV absorbance of most triterpenoid saponins, we propose to use a mass spectrometry detector for its identification.